Okay, so good afternoon, everyone. We have the pleasure to have Professor Adriano Pieres from Rio Grande do Sul today. Thank you a lot for accepting this invitation, and it's going to talk about the Magellanic Clouds outer regions. So please go ahead.
Thank you, Vinicius. Good afternoon. I'm PhD student Adriano Pieres, and I'll present a work about the Magellanic Clouds outer regions. Thank you, Vinicius and Linea team for the invitation. The main topics for this presentation is related to the Magellanic System, the Magellanic Clouds, the Bridge, and the Stream, and its main related published papers. In the second part for this presentation, I'll show the results for the search for stellar clusters in dark energy survey science verification images. Here we can see the sky at night. As we can see in the V-band, clearly the Magellanic Clouds are visible as the main features in the southern sky. We can see the large Magellanic Cloud, also the Small Magellanic Cloud, and here is a faint dot is the M31 and the galactic center. In the IRIS infrared 100 micrometer band, we see the galactic plane parsec from the sun, comparing to M31 located at 700 kiloparsec. They are very close to us and with a large angular size. I'm listing here the main features for the LMC and the SMC. They are classified as irregular. If an LMC has a disk, a bar, and a sketch for a spiral arm, as you can see in the figure on the left. The LMC center differs if you consider isophotes, HB stars, or nuclear atomic hydrogen gas. The SMC, as classified as an irregular galaxy, has also a disk, a bar, and its mass is about 1/10 of the Large Magellanic Cloud, but its shape is more irregular than the LMC. In the image in the right, we can see the SMC and also the Galactic Globular Cluster 47 Tucana. Here I start to present the more recent works and more significant works about the Magellanic System. Using UGO data, the Magellanic Bridge is clearly seen as an overdensity made of young stars. The paper published by Skuro shows the distribution for young population, red clump stars, and red giant stars. In the panels in the right, the LMC is the white ellipse located in the left, and the SMC is the smaller ellipse on the right. Using a CMD mask, they plot the distribution of stars, and in the first panel, the young stars tend to link the SMC and the LMC more than in remaining panels, where the red giants are more concentrated in both galaxies than in the Midway. The Magellanic Bridge is basically a young structure formed about 200 million years ago. The paper from Bika and collaborators found very young clusters, and the oldest stars in their sample agree with the simulation from Diaz-Ibeki 2012. However, Baggery and et al. Listed candidates for old stars in the bridge, mainly as debris from a recent LMC-SMC interaction. Also, neither present a bimodality in red clump stars. In the eastern SMC fields, here highlighted by a solid red line in the figure on the right. They sampled the SMC stars in Magellanic Clouds panoramic survey. The Magellanic Stream is a large structure covering 200 degrees in the sky. Even large, it's a relatively young structure dated on a few billion years. This stream was detected in 1965, but the link to Small Magellanic Cloud and Large Magellanic Cloud was settled just 10 years later. There is no stellar counterpart to the gas in the stream as probed by Guhathakurta and collaborators in a deep, very deep, reaching R magnitude equal to 27, but in a restrict field, 5 by 7 arcminutes in the Keck telescope. Also visible in the figure on the left is the leading arm as a gas structure in opposite side to the Magellanic Stream. The Magellanic Stream is in the bottom and the leading arm in the top. Searching for debris in Magellanic Stream, we filter the stars in DES Y2Q1 catalog with the same metallicity, the same age, and the same distance than SMC old population. But we didn't find any stellar overdensity associated to that stream. As you can see in this figure, the Magellanic Stream is based on this region, but we didn't find any stellar overdensity here. For the future, maybe a better Milky Way subtraction could improve these results. In this slide 10, a very interesting paper from Olsen 2011, 5 years ago, is about the radial velocity for the LMC stars. Using a large sample of giants, they corrected the radial velocity by the LMC systematic velocity. In the figure in the left, the stars are color-coded by the velocity, and the stars in the northwest region, or top right, are at mostly stars that are moving away from us, and in the southwest, the southeast, the stars are moving toward us, the stars in blue color. But 5% of the sample is a counter-rotating stars. The median metallicity for this kinematically distinct population is lower than the median metallicity for LMC stars, and agree to the SMC median metallicity. The authors support the idea that these stars are striped from the SMC in a recent outcoming. A star-forming region in LMC is the Tarantula Nebula, or 30 Dorados, highlighted here by a blue ellipse here. With an absolute magnitude in V-band about -10, this is the most active starburst region known in the local group. Therein, the most massive stars are forming in a region of 500,000 solar masses. Crowther and collaborators found a mass greater than 300 solar mass for the most massive star. The Magellanic Clouds' proper motion were determined very recently by two main authors, Vieira, 2010, and collaborators, and Liu in 2006 and 2013. Vieira collaborators compare photographic plates and CCD images in a wide region covering both clouds and 40 years in time, as we can see in the top figure. Their results are compared to 3 Liu papers using HST images. In the bottom image, the results are compared among another results. The Vieira results are the solid black line for the proper motion for the LMC and for the SMC. Liu 2006 are the dotted ellipses, and Liu 2013 results are the blue ellipse for the LMC and for the SMC. The results from Vieira agree to the results from Liu as a mean value. An interesting result from Vieira is that clouds are in the limit for binding energy, and Liu states that the clouds are most probably in their first infall towards Milky Way. In this image, we can the present work here is the simulation for presented by Gyrs and Becky, which I will present in a few slides ahead. Regarding the RR-Lear variable star distribution, Klein and collaborators presented a three-dimensional map using UGO data and over 15,000 variable stars. The distance is determined by the periodic luminosity relation for RR-Lear. The distribution presents an oblate shape even in the LMC center, with the major axis pointing towards Milky Way, probably due to Milky Way gravitational potential. This slide presents the work from Masking and collaborators. They present the star formation history for 3 fields in the outer LMC regions, distance for 5.5 and 7.1 degrees from the LMC center. A clear outside the information, we can see in this plot, outside in star formation, and a quiescent period between 7 and 4 gigayears ago can be seen in the results, and the star formation is more efficient in the inner regions than in the outer regions. Also, a significant paper is the paper by Harris and Zaritsky 2009 with 20 million stars in Magellanic Clouds photometric survey. They present an initial burst for star forming, a quiescent epoch between 12 and 5 gigayears ago to both clouds, and sharing sets for star formation in 500 megayears and 2 gigayears, evidencing for LMC and SMC a joint history. The N-body simulation from Diaz and Becky 2012 is presented in the leftmost panel. Here is the simulation. Here is the real distribution of gas in the Magellanic stream. The Magellanic stream presents 2 filaments here, and we can see in the simulation also both filaments presented. And another important or significant structures like this triangular shape in the simulation are roughly presented in the real data. In the top right figure, we can see two men oncoming between SMC and LMC at 250 megayears and 2 gigayears ago, here and here. In the bottom right panel, the evolution of SMC along time, where the Magellanic Stream develops starting from an SMC spiral arm. As you can see here, the A, and it turns to the Magellanic Stream. I think this is the last paper that I'll present here before our paper. Still considering the SMC, Midway 2011 sampled stars in Magellanic Cloud panoramic survey. In the left figure, we see the fields sampled in that survey. The fields sampled with shallow photometry in red and the deep photometry in another color. The giant star density is plotted on the bottom right figure, where they fitted a new center for the SMC. They have found an exponential profile extending out to 7 degrees from about 7 degrees from the SMC. Beyond that, there are density fluctuations, maybe due to bound star halo or to extratidal stars. Well, starting from now, I'll present our work about the LMC clusters in dark energy survey. This is an introductory slide about the dark energy survey, showing its footprint in the end of the survey. The outer Magellanic Clouds region, as you can see, for the LMC, the outer regions are presented more in the science verification data. The science verification data have the same depth as the end of the survey. Here we can see also the bands for dark energy survey. And here we are dealing with the science verification images, mainly in the SPT, this region that is called the SPT East. Summarizing our work about the stellar completeness in only one figure, that's the figure on the left. We determined the stellar completeness, that the stellar completeness is decreasing with the star density. To solve this problem, we implement a pipeline based on DAO fault to reduce the images around each cluster candidates that it was visually identified. So here we are not using the dark energy survey catalog to sample the cluster candidates. We are just using to determine 0 points, and we are reducing each G, R, and I images. Please, if you have a question, tell me. Basically, to identify the LMC clusters, we implemented a visual search in science verification tiles. After that, we listed 255 stellar overdensities. We matched these overdensities to BICA 2008 catalog, where we identified 146 clusters. We identified also 109 new candidates. We implemented maximum likelihood approach to fit profiles and models. In the end of this approach, we fitted 124 profiles for these overdensities, and after fit the profiles, we fit the isochrones or the models for these overdensities, and we find 117 clusters with fit isochrones and profiles. In the end of this work, we'll have 28 confirmed and unlisted or unknown stellar clusters unlisted in any previous catalogs clusters. These are, the figure shows the distribution for the sample of clusters that we have found. To determine the profile, the stellar density profile, we compare the stellar distribution to a King profile.
What is the, sorry, so what is the color code? Sorry, Adriano.
This is the tidal radius in parsecs.
Okay.
So we use the King profile to determine the structural parameters for these clusters. We determine the center and the core radius and the tidal radius. In a short way, we determine the star counts, the two overdensity, the M stars. After we determine the key parameter that is related to the density of the cluster, and in a likelihood approach, we determine the best set of structural parameters for that overdensity. Here I present an example for a cluster. The top panels in the figure on the left shows the likelihood for core and tidal radius and for the cluster center. On the right, we use a profile analysis technique, letting the likelihood flows instead fix the remaining parameters at the best value. For 1, 2, or even 3 sigmas, the differences between the two methods are very small. To compare our sample of clusters to models, we apply the same technique, that is the maximum likelihood technique. We compare the set of stars with likelihood to belong to the cluster greater than 5% to the Bresson models. So we can determine the most likely isochrone, determine the age, the metallicity, the color excess, and the distance models. The figure on the right shows an example for this comparison. That is the likelihood, and the color, the stars in the CMDs are color coded by the likelihood to belong to the cluster given by its profile. Before apply to the LMC cluster candidates, we applied the technique to simulated clusters. We simulated clusters using GEM CMD, following the same steps for the real clusters. The figure here is one example for to recover the structural parameters. Also, again, the King profile are applied to determine these cluster parameters. This figure is one example. Instead, applied to just one cluster, we simulated a set of clusters. Here is the recovery, the difference between the inserted parameters minus the recovered parameters divided by the inserted parameter. So simulating many clusters and comparing the differences between the certain parameter and the recover parameter, we can determine where we can rely, we can trust on the results, and a limit where we cannot trust on these results, based on the richness or the star counts to each cluster. The minimum star counts for simulation are 38, and the real cluster richer than 38 stars have 44 stars. We note that the age and metallicity are very well recovered, and the error for the remaining parameters decreases as the star counts increase. So we apply this number for the real clusters as 44, the 44 stars. Comparing to the literature, we do not basically we do not have a bias in our determinations. The literature basically poor for this outer sample and presents a high spread among authors. For the clusters fitted by isochrones, the models are older than we are comparing to. In the sense, in summarizing, we can approve the methods for this comparison. Here I present, I think, one of the most significant results for our sample. We have two peaks for the age distribution at 1.2 and 2.7 gigayears. We we applied two Kolmogorov-Smirnov tests, one comparing this sample to a sample to 1,000 samples made from one Gaussian. The hypothesis test indicates that we can reject one Gaussian and we can accept two Gaussians. The tests using Ashman and 1994 approach is not indicated for this sample because this is an heteroscedatic sample. It's not an homoscedastic sample. Applying GMN, or the Gaussian mixture models, this test indicates that two Gaussians are the most indicated for distribution. And regarding the distribution along a radial coordinate, there is no a radial trend in age for our cluster sample. But regarding metallicity, we have a gradient. We have a peak in metallicity distribution in minus 0.9, and hypothesis test indicate that there is a real radial metallicity gradient. The metal poor clusters are scattered in the entire radius, and the metal rich clusters are more concentrated in the inner regions. In the last but one slide, I compare the age-metallicity relation from our sample to Piatti and Geisler 2013. Their field and cluster star sample are located in the LMC inner regions, and in the age-metallicity relation, the field stars and cluster sample are outlining an upper envelope regarding our sample. Basically, this is due to the Piatti and Geisler sample. Piatti and Geisler sample are located in the inner regions and a more metal-rich region than our outer regions. Comparing our cluster sample to Pageau and Tautzweisian in 1998 analytical models and Harris and Zaritsky 2009, the clusters are located in the Midway. The Harris and Zaritsky 2009 are represented in a dashed red line, and the Pageau and Tautzweisian in this solid green line. We can see that the older cluster, here we have the reticulum cluster and a cluster listed by ISO 121 SCO3. They tend to agree better to the Pageau and Tautzweisian in 1998 model. And for the younger clusters and more metal rich, they tend to stay the midway. The spread in the metallicity for the clusters younger than 2 gigayears can be explained by the insert of the SMC gas as simulated by Gyrs and Becky 2012. We can note also a clear increase in metallicity for the cluster samples, for the cluster sample in the recent 2 gigayear, compared to the period between 10 and 4 gigayears. Basically, these are our results about the age-metallicity relation. So, that's it. Questions? Thank you.
Okay, thank you very much. We have time for questions. So any questions?
Adriano?
Yeah, jogando.
How is the new data to bridge the gap between new detections and the clouds
the age gap
coming along
for the LMC?
Yeah.
We have this this cluster, and basically the age gap is the period between 12 or 10 gigayears and 4 gigayears. We have just one. This is the so-called emblematic cluster ISO 121 SCO3. It's located in the gap, but the gap is not a rigid barrier. Yeah, it's this cluster belongs to the older sample, older LMC cluster sample. So we preserved this. We didn't find a cluster in this gap, with the exception of this cluster. Okay.
Okay.
More questions?
I don't know if I missed it. Do you have a sense of what to expect from year 3 in terms of discoveries of new satellites or new candidates?
Year 3, I think that we can go deeper in year 3, but I don't think that the footprint is wider or greater than in year 2. So maybe we can explore the limits in the depth.
So you're saying you wouldn't expect new candidates of satellite galaxies?
I think that I expect new candidates, but I don't think something like 8 or 9 or 7, maybe confirmed 1 or 2.
Okay, thanks.
Okay, more questions? Okay, so I want to thank you, Adriano, again. Thanks a lot for this nice talk, and thank everybody for coming. So,
Bye-bye.
Okay,